Our story begins not with complex equations, but with a simple yet profound human idea. Imagine, for a moment, a world without numbers. How would you track your flock, measure your land, or even know how many days have passed? The story of mathematics is the story of humanity's quest to answer these questions, a journey of ever-increasing abstraction, where each step away from the concrete world, paradoxically, gives us a more powerful way to understand it. Let's travel back in time, tens of thousands of years. The first mathematical thinking wasn't about numbers as we know them, but a more basic concept, one-to-one correspondence. Early humans used notched bones like the 40,000-year-old Lebombo bone as simple tallying devices. This was the first great leap, abstracting the idea of how many from the things being counted. This cognitive shift eventually led to the rise of the first great civilizations in Mesopotamia and Egypt. As societies grew more complex, so did their needs. Mathematics became the essential tool for measuring land, calculating crop yields, and managing trade. It was the bedrock of law and order. Interestingly, these two civilizations developed remarkably different systems. The Mesopotamians, using clay tablets, created a sophisticated base 60 system. Its genius lay in its divisibility, making fractions for commerce and astronomy incredibly simple. This is why we still have 60 seconds in a minute and 360 degrees in a circle. The Egyptians, on the other hand, developed a base 10 system, rooted in our 10 fingers. While intuitive, it was less efficient for complex calculations, yet their practical mastery of geometry is evident in the breathtaking precision of the pyramids. For centuries, mathematics was a practical tool, but then something changed. The ancient Greeks inherited this wealth of knowledge, but began to ask a new, revolutionary question. Not just how these rules worked, but why they must be true. This transformed mathematics from a tool for bureaucrats into a philosophical quest for eternal truth. This intellectual revolution was sparked by figures like Thales of Miletus, who introduced the concept of deductive proof.
He insisted that geometric statements must have a general, logical justification. This new approach was passionately embraced by Pythagoras and his followers, who believed that all is number and that the entire cosmos was governed by whole numbers and their ratios. This worldview was shattered, however, by a shocking discovery from within their own ranks. The square root of 2 is an irrational number and cannot be expressed as a ratio of whole numbers. This crisis dethroned arithmetic and elevated geometry as the foundation of Greek mathematics. This focus on geometry reached its zenith with Euclid of Alexandria. His masterpiece, The Elements, organized centuries of Greek mathematics into a single, rigorous, deductive system built upon a small set of definitions and axioms. For over 2,000 years, it stood as the paradigm of mathematical reasoning. The era's greatest mind, Archimedes of Syracuse, then pushed the boundaries even further. Using the method of exhaustion, a forerunner to modern calculus, he calculated the areas and volumes of curved figures with incredible precision, all while adhering to the strict logical standards set by Euclid. As the classical world waned, the torch of mathematical innovation was carried eastward, first in India and then throughout the Islamic world. Indian mathematicians made monumental contributions, including the concept of zero as a number in its own right, and the decimal system we use today. From the 8th to the 13th centuries, the intellectual heart of the world was the Islamic Empire. Scholars in Baghdad's House of Wisdom translated and synthesized Greek and Indian knowledge, forging a new, more powerful mathematical framework. The most influential figure of this era was Al-Khwarizmi, whose work on systematic algorithmic procedures for solving equations gave us the word algebra, and, from the Latinization of his name, algorithm. He treated rational numbers, irrational numbers, and geometric magnitudes as abstract algebraic objects, a crucial step toward modern symbolic math. This rich body of knowledge began to flow back into Europe, most notably through Fibonacci, who introduced the Hindu-Arabic numeral system to a European audience, setting the stage for the next great leap forward. The reintroduction of this knowledge, amplified by the printing press, ignited the scientific revolution. The world was no longer seen as static, but as a dynamic system of motion and change, requiring a new mathematics to describe it. This era saw the development of modern symbolic notation, with symbols for plus, minus, and equals, freeing algebra from the constraints of words. This new symbolic power led to a grand unification: analytic geometry, created by René Descartes and Pierre de Fermat. By linking algebra and geometry through the coordinate system, they created a dictionary to translate between the two, allowing geometric curves to be expressed as algebraic equations. This was the language needed to describe a universe in motion. The ultimate tool for this task was calculus, invented independently by Isaac Newton and Gottfried Wilhelm Leibniz. They developed methods to analyze instantaneous change and the accumulation of continuous quantities, finally resolving the ancient tension between the discrete and the continuous. Their crowning achievement was the fundamental theorem of calculus, which revealed the profound inverse relationship between differentiation and integration, unifying the two main branches of calculus into a single, incredibly powerful system. The incredible success of calculus led to a new period of introspection in the 19th century. The methods had often been applied with more attention to results than to logical soundness, and a conviction grew that mathematics needed to be rebuilt on more secure, rigorous foundations. This pursuit of rigor, led by mathematicians like Cauchy and Weierstrass, led to precise definitions of limits, continuity, and the real number system itself. But this quest also opened up strange new worlds. For 2 millennia, Euclid's geometry had been considered the one true geometry of space. But mathematicians like Gauss, Bolyai, and Lobachevsky dared to assume one of its core postulates was false. To their astonishment, this led not to a contradiction, but to new, perfectly consistent, non-Euclidean geometries. This discovery was philosophic dynamite. It severed the unbreakable link between mathematical certainty and the physical world, redefining mathematical truth as a matter of internal logical consistency. At the same time, the French genius Évariste Galois invented the concept of a group to understand the deep, underlying symmetry of equations, giving birth to abstract algebra. And then, Georg Cantor ventured into a realm previously considered paradoxical, the infinite. He developed a rigorous way to compare the sizes of infinite sets, proving the stunning fact that there are different sizes of infinity. This explosion of abstraction, however, led to a crisis. Cantor's set theory, intended as a foundation for all of mathematics, was found to contain contradictions, most famously, Russell's paradox. The entire structure of mathematics seemed to be built on shaky ground. The leading mathematician of the era, David Hilbert, proposed a grand program to formalize all of mathematics in a single, complete, and consistent system to banish all paradoxes forever. But in 1931, a young logician named Kurt Gödel shattered this dream. His incompleteness theorems proved that in any sufficiently powerful system, there will always be true statements that cannot be proven. Mathematics is inherently, eternally incomplete. Furthermore, no system can prove its own consistency. While a blow to the quest for absolute certainty, Gödel's work was also a profound liberation, showing that mathematics is an open, endlessly creative endeavor. It was in trying to answer these deep questions about the limits of proof that the British mathematician Alan Turing conceived of a theoretical model of computation. the Turing machine. This abstract, programmable, symbol-manipulating machine is the direct theoretical ancestor of the modern computer. The digital age is thus a direct and practical consequence of the most abstract inquiries into the limits of reason. This brings us to today. The journey of mathematics has come full circle. The most abstract, esoteric branches of thought are now the indispensable tools of the modern world. Topology, the study of properties preserved under continuous deformation, where a coffee cup is the same as a donut, provides a language for the fundamental structure of space. Cryptography, which secures everything from our banking to our emails, is built on number theory, once considered the purest and most useless branch of mathematics. And modern artificial intelligence is fundamentally an applied mathematical discipline, built on a synthesis of linear algebra, calculus, and probability theory. The story of mathematics is far from over. Great unsolved problems, like the P versus NP problem, which asks about the fundamental limits of computation, and the Riemann hypothesis, which concerns the distribution of prime numbers, continue to drive research at the frontiers of human thought. The unfolding tapestry of mathematics, woven from threads of practical necessity, philosophical curiosity, and pure aesthetic delight, continues to expand in new, beautiful, and unpredictable patterns. It is, and always will be, an endless frontier.